Welcome back to Beyond the Patterns. Today I have the great pleasure to introduce Zongwei Zhou. So he is currently postdoc at Johns Hopkins University, graduated his PhD in 2021 from Arizona State University, and is very, very active in the medical AI community. You can see that he has published more than 30 peer-reviewed papers in top venues like IEEE TMI, has received several outstanding research awards like the MedIA Best Paper Award in 2010, in 2019 the Mikai Young Scientist Award. So he is very, very active in the field, and also he was named, by the way, as a top 2% researcher by Stanford University in the years 2022 to 2024. So it's really a pleasure to have him here for an invited presentation. It's entitled Body Maps Towards 3D Atlas of the Human Body, and you will see that he is working really in a big network of researchers that are providing large databases for training medical AIs, and I'm very, very happy to have him here. So Zongwei, the stage is yours.
Thank you very much for the kind introduction, and it's a really honor to be here and to share our recent work. I'm currently a research scientist at Johns Hopkins University. So recently we have an initiative in JHU. It's a data science and AI trust dataset. The aim is to provide the leading source of database for research and the development of trustworthy AI system. And our research group is creating large-scale CT database by having medical professional and engineering expert working together to annotate human anatomy and detect the disease in the CT scan, and make sure this dataset can be public available for the research purpose. Because there's a whole bunch of reasons the medical data is very difficult to share across the world. So why annotating human body is so important? Let's take a look at how we understand the Earth. Human has been creating maps of the Earth thousands of years. Satellite images begin being used from 1960. This is a satellite image of Johns Hopkins CS department building. But you see there's not many useful information from the raw image data because before you annotate anything. And what Google did is they annotate the building, the glass, the tree, the mountain, and to start to make this image make sense and can be used in the daily life. And further, they create knowledge from this map, so we can make a decision how we go from this point to that point. And this leads to a lot of real-world impactful applications, such as Lyft, Uber, and maps. We are asking question, can we do this to understand the human body as well? Because human internal structure is also very complicated, and it's better to be understand to keep us from the disease. So we use the CT scan as an example. You can see if you are not expert in medical, to the high school or graduate student, maybe you have no idea what this image is about. And if you can annotate the image, which one is the organ, which one is the vessel, and the bone, and so on, you pretty much have an understanding of what is really going on in my body. And you can render and make some knowledge from it, make a medical decision, measurement of the tumor, and so on. It can lead to a lot of exciting applications, such as virtual reality, and it can improve the patient communication and improve the AI for medicine. Google tried to map the Earth, and we aim to map the human body. We try to make the AI understand each organ, the anatomical structure, and even for the disease, make a 3D understanding. There's a related work in last century. It's called the Visible Human Project. Basically, it used the real human body. They cut it and they store. You can visualize the two-dimensional slice of each view of the human body. So this is a way to visualize what is really inside. And this has been really useful for the visualization and for the medical education. However, this project have a limitation because it's only provide two human body sample, one for visible human male and another for female. So this data set is not personalized for each individual. So the visualization is not actually me, you, and anyone. And also, this data set is a copy of dead body. So many anatomical structure might be different from the real world patient. Fortunately, we have a computed tomographic image. So this is commonly used nowadays. You get into the machine and the X-ray can tell you what's really happened inside the body. So we try to use this as the raw body because you can map the human body for each individual patient. Now we have the data. The most expensive part is to annotate this data to make sense for the human and for the AI, for the computer. Usually, you train the AI, it will require per voxel annotation. As I showed before, you give a contour for each anatomical structure. Not everybody can do this work. It's different from computer vision. Everyone can tell you which is cat, which dog, and they can annotate the street, the building for you. Medical image annotation really need expert knowledge, especially when you annotate the disease or the cancer. It's sometimes even need the biopsy result. It's very difficult to get. So we have the body map 1.0. So this version is mostly focused on the abdomen region because in this region, we have most complex anatomy and many diseases are associated with this area. And it's extremely important for early detection of cancer. We call this database as abdomen atlas. And you can see on the left, it's pretty much like a map, a human map. So it's each island and tell you which is which. And it's really helpful if you have a huge database, it can create a strong AI that be generalizable or robust to many new CT scan and help reduce a lot of human work. So this talk will be this talk's structure will be a little bit different from other talks because I will present first what we already achieved, then dive into how we did it. Because annotating high-quality dataset is a very time-consuming, difficult, tedious work, require a lot of collaboration to the medical professionals and computer science people. So to be honest, this huge task is not very suitable for the student at the early stage. But once the dataset is created and available out there, they can encourage many scientific discovery and AI development. We present Abdomen Atlas. This is the large-scale, multi-institutional dataset with detailed per voxel annotation. Large scale because it provides more than 25,000 CT scan of 600,000 3D mask of human body. These scans are collected from 112 hospitals, 19 countries. It's very diverse. And we provide high quality 3D mask for 135 body compositions in every scan. It includes 34 abdominal organs and their subset. So here we also provide the liver subset and the pancreas subset, head, body, and tail. This is important for the tumor study. And the 19 chest organ and several vascular structure and skeleton structure. These scans are very different in terms of patient demographics, imaging protocols, scanners, and this also include a lot of pre-existing datasets that's already public available. To create this huge database, we have a team up with 13 expert radiologists and a lot of medical trainees. Let me give you a rough idea how long it will take to annotate one organ. For example, liver, it usually takes a radiologist 13 to 16 minutes to finish one patient. And the annotation time will increase if the structure is very complicated, such as column. Annotating a column per voxel, it will take up to 3 hours to complete. So the big annotation cost is the key reason why most public available datasets are single-centered and limited in size and biased. Of course, another reason is the patient privacy issue is IRB, but that's doable. But the really problem is annotation. It's really expensive. Look, if you try to annotate the scale, the dataset with a similar scale as us, 25,000 CT scan, 600,000 3D mask, guess how long you would take if you don't have an innovative AI algorithm to help you? A radiologist, one single radiologist will be working on it since 1790. It's the first time the DC becomes the capital. And he will finish the job last year. And this clearly not possible. It make the people half crazy already. So to accelerate this process, my research is to create an innovative algorithm to integrate AI and the radiology together to speed up. And we call it ScaleMine. So the idea of dataset creation and AI development, so far, most people treat it as an independent and a subsequential step. You first create a dataset, then you release it, you train the model. But we think this is super unnatural because on the one side, the dataset creator, they don't know how much data the AI people need. And on the other side, AI people really want to help the radiologists to speed up their work because AI nowadays can do a pretty good job to produce the pseudo annotation for some organ like liver. It's quite easy. The DICE score is already above 98. So we create this AI integrated framework to combine the radiologist with computer science together to build this database together instead of make it 2 steps. So it first have the clinical need. For example, in our case, we want to detect the cancer from all the organs. And then we find the suitable data. So here we use the large language based because from my experience, the most search engine in the clinical setting is not very accurate. And now the language model get into the picture, they can do at least the high school student level job, and the search for these keywords can be really more accurate than the conventional search engine. And then we integrate the AI, the vision language model, and the human together to become a human-in-the-loop annotation pipeline. And here we have several innovative structure I will introduce later. And this can improve the annotation quality, and we select the most important data. This means the data that can help AI to improve the performance the most. So here, not every data point is equally important. So most data are duplicated. So here we have a entropy-based way or diversity-based way to select these important data. And we also create a synthetic data because the real world data is biased. It may not give you all the distribution that cancer can locate or cancer size. So synthetic data is important. And we also use the unlabeled data. We put everything together into the AI algorithm. And this in turn will help go back to the human in the loop to help improve the efficacy. So two main strategies. One is the test on training. We want to reduce the human effort for the annotation. So the insight is when AI struggle to fit a specific data point in the training set, it often means your training set have the label error because AI is extremely good at overfit the data point. If it cannot overfit this data anyway, most likely your data have the error. So this is a very effective way to quickly find the label error in your database. The second is we create a label expert because as said, nowadays the large language model, the large vision language model can do pretty good job. And you see, if you tell the model what's the anatomical prior of one structure should look like, it can give you an answer which annotation is better quality. So here we have a CT scan, we have a label candidate 1 and a label candidate 2. And the model's job is to tell me which one is better. So in order to create this pseudo label, we can always use the AI prediction. And we prompt the vision language model, okay, tell me which input is better. And here is some background of this structure. This is alta. So alta ought to look like this. The alta should appear as a long vertical red line with a curve at the top. Then it can automatically give me the better preference. And compare with the manually check label one by one, which will take 5 minutes per scan. Label expert can reduce this to 5 seconds per scan. And it can tirelessly compare 35 millionth pair of label candidate. And you know, the vision language model can work 24 hours, 24/7. So ScaleMine not only can produce new dataset, but it also enhance the existing dataset. I guess you guys know the total segmentator. They also produce pretty high quality database, but for some class, the annotation might be have some noise, and the ScaleMine can quickly figure this out. And this work have been featured in J2 News. AI and the radiologist unite to map the abdomen. We released this dataset under a non-commercialized license so that it can be widely used for research purpose. You can download all versions of dataset from this website. We also have an official XCount to showcase in our database, along with the medical notes written by radiologists. We update it in a weekly basis and will also make an announcement when newer version is released. So After annotating the body compositions in abdomen atlas, we turn to a harder task, which is the tumor annotation. Tumor is very different because it's a very widely in size, shape, and location, and it often require pathology report to confirm the type. This makes them far complex than what I introduced before, the organ segmentation. And our goal is again to create a huge tumor database like everybody needed that can public available. And you might know, even for the institute like JHU, annotating tumor is still a painful headache. So before we really dive into create a big, very expensive data set, we did one thing. We did check how many data is really needed for training a reasonable, like good AI. We want to know the minimal requirement to control the cost. So we start with an internal data set at Hopkins. This data set take 5 years to create, and it's already done when I joined Hopkins. So I can directly use it. This data set have more than 5,000 per voxel annotated CT scan. That is 3.8 million CT slides with a pancreatic tumor. And this, we also have a per voxel annotation of the tumor type. It includes the pancreatic cyst, PDAC, and PNET. AI trained on this huge database can achieve performance comparable to expert radiologists, especially for the small tumor detection. So we want to use this dataset to know what's the minimum requirement to annotate a dataset. Of course, 5,000, it's very, very expensive. So first, in order to check if the AI really achieves the human performance, we did a reader study because we don't want we have a minimal number and it turns out the AI cannot achieve a very promising performance. We want the AI can at least achieve the human level performance. So we did a reader study on this data set. We have 6 junior and 5 senior and 2 expert radiologists in this study. And they are told to take a look at the CT scan and to detect the pancreatic tumor if available. And they are told to classify the type of the tumor. Here's the result. On the left is the detection result, the RC curve. The red line is the AI, and all these dots are radiologist performance. So you can see the AI trained on 5,000 annotated CT scan can achieve almost a similar performance to radiologist. And interestingly, here the confusion matrix, if you look at the accuracy of classifying each subtype, AI can achieve even better performance than radiologist. So this is a very encouraging result. But here, a radiology report result is a little bit lower than what they can achieve in the clinical practice because in our study, they cannot access the patient history or other biopsy result. So, but anyway, this AI, it's a promising AI for at least pancreatic tumor detection. Then having this in mind, we know if we train AI on 5,000 scan, it can achieve performance we're happy with. Then we start with the scaling down experiment. You always hear the scaling low, the scaling up and up. But now we are doing the scaling down to see what's the minimum number that we need to annotate to let the AI have this performance. So it turned out to be the 5,000. So if the randomly select the 5,000 sample, the AI can achieve similar performance. But this can be improved because this 5,000 can be carefully selected. You can do some analyze to select a very diverse 5,000. Here's a 1,500 sample. And maybe this number can even go push down. So we even 1,500, we think it's quite a lot of work, to be honest, because our goal is to annotate all cancer in the human body, and 1,500 it's still a lot of work. Then we look into the possibility: can we push this number even smaller by using synthetic data? Synthetic data has been popular recently, especially the computer vision. And many generative AI, they can create very beautiful, realistic images. And sometimes they show some kind of compositional ability that create the image that never happen in the real life. The problem is this generative model is at the moment is not very good at generating medical data. So I just did some tests recently to ask the model to create a liver without tumor and the liver with tumor. So this is a result. You can see it's nothing like the real CT scan. But we still think the synthetic data have the big potential because it's free and it's perfectly labeled. You can condition the mask that you want the model to create. That means you can have the paired image and the mask at the same time. And the synthetic data will not have the privacy concern, and you can essentially create as many as you want. So at Hopkins, we try to create the synthetic data since year 2023. It has been really successful, and the conclusion is that if you only trained on synthetic data, the AI can achieve the similar performance compared with you trained with real data. And if you can include the synthetic data into the real data for training, it can significantly boost the performance. And synthetic data have an advantage in early stage cancer detection that I will describe later. And there are other works on this data synthesis. The NVIDIA last year, they released a model that can create the synthetic image of the entire human body. And you can see, based on the segmentation, the NVIDIA's model can create quite realistic CT scan, but the limitation is they are still not quite well in creating the tumor. So our team, it's almost the first team that created the realistic tumor in the human body, including the liver, pancreas, and the kidney organ. The observation why we can create such a realistic tumor is that early stage tumor, less than 2 centimeters, often have a similar appearance in CT image, whether they are in liver, pancreas, or kidney. So here's some example how the tumor look like in different organs. So keep this in mind. We use the diffusion model to learn from one organ tumor and create the tumor in other organ. So diffusion model, you might know, it have the limitation. It need a lot of data to train. That, in another word, it's very easy to overfit the specific data point. This is a disadvantage, but in our work, we make this advantage because if you can overfit the tumor and the observation is the tumor looks similar across the organ, then we can use the diffusion model to repeatedly create the similar tumor across the organ. So this actually really excites for innovation, and it can help us to create a lot of tumors in these organs. And you can see they are all similar if you only look at the tumor region. Of course, the surrounding organs are different. So to back up our claim, early stage tumor, they look similar across organs. We did some reader study. So here we mix them up and ask the radiologist to tell us where these tumor are come from. And you can see the performance not very good. It's equal to random guess. So even radiologists only look at the tumor appearance, they cannot tell where it come from. And we also train a machine learning classifier to classify the radiomics, the feature of this real tumor. It's also similar to the random guess. And we plot the TSNE on the radiomics feature and see they are pretty much overlap in terms of the space. So this back up our claim that the tumor at the early stage, they look very similar across the organs. And we also did a fun reader study. It's called the vision tooling test. So we mixed up the real and the synthetic tumor and asked the medical expert to tell which one's real and which one's synthetic. And the result shows the junior radiologist, they can achieve almost the random guess accuracy, 50% chance to be correct. And for the senior radiologist, they can achieve 70% accuracy. So you can look at this and see if you can tell which one is real, which one is fake. Actually, this is a tricky test because all these tumors are synthetic. And having this in mind, our teams have been focused on creating realistic but synthetic tumor for years, and we have made good progress. So if we add the synthetic data into the real data, we can push this number even further to 500. That means you only need 10% of the expensive dataset. You can achieve the human level accuracy of the pancreatic tumor detection. This is really encouraging because this makes the task doable. So if we want to annotate tumors in 6 organs, we only have to annotate 3,000 samples. That's a manageable amount. So we are proud to present the next edition of Abdomen Atlas, a dataset of over 10,000 CT scans with a total of 8.5 thousand tumor instances per voxel manually annotated in 6 organs. And this includes the pancreas, liver, kidney, colon, esophagus, and the uterus. And we have a 5,000 non-tumor scans as control. Each of these scans are associated with a tumor report, and this report will tell you the tumor size, tumor location, tumor shape, and attenuation, and pathology types. Our report have more than 1.2 million text tokens, and it's really useful for the visual language research. The creation of this dataset involves 13 expert radiologists and many medical trainees. Currently, no public available dataset of this kind exists. We are in the progress of making this dataset fully available to the public and we expect to make it public by the mid of this year under a non-commercial license, and we are happy to offer early access to a few research groups together for the beta test. Actually, we already did for several of them. Yeah, you can contact me if you are interested. You might wonder how we can annotate so many tumor scans in a short time. 6,000 is still a big number. So we have two recipes. The number one, synthetic tumor. Number two, RC analysis. We first train AI on existing public but very small scale tumor dataset, and supplement by training AI on as many as synthetic data as possible. Then we have the sensitivity and the specificity. They are usually balanced if you adjust the threshold. But in the data annotation, we do not really need a balanced sensitivity and specificity. We intentionally change the AI threshold to have almost the perfect sensitivity, 99%, 99.99%, and acceptable specificity to make the AI overly sensitive. Why is that? I will explain later. But if you make it overly sensitive, you will increase a lot of false positives. But we like false positive in this specific scenario. So if you have a very high sensitivity, that means the AI will almost never miss any tumor. So, but it will generate a lot of false positives. So handling false positive is much easier in our annotation software because the radiologist only to click only one click, it can remove the entire 3D false positive. So here, one click, 1 second. So our strategy is first to use a radiology report to tell us whether this CT scan have the tumor or not. So radiologists are always available in the clinical data repository. For the CT scan without the tumor, we can automatically remove all the false positive without any human intervention. For CT scan with tumor, after we change the AI threshold, we have a very high sensitivity. That means that all the tumors already per voxel annotated, and you only have to manually remove the false positive. And our algorithm can give you a AI model of 99% sensitivity with 0.6 false positive per patient. That means the radiologist only have to deal with one false positive, remove one false positive every 2 patients. This is much quicker than create the tumor mask from the scratch. So we demonstrate the usefulness of our tumor abdomen atlas dataset by the use case of a pancreatic cancer detection, and we achieve a similar performance to the expert radiologist. And especially, it's very good at detecting small tumor because the synthetic data can give you as many as a small tumor as you want. So our AI can achieve 89% sensitivity for detecting this small tumor, and compare with the human performance, it's only 33 to 44% for the small early detection. And we can detect the tumor as small as 2 millimeter. And our AI algorithm is robust to different quality of CT scan. So our dataset have the diagnostic CT, which means it's a high quality in the training. But when we test on the lower resolution CT, it's a planning CT, its performance still robust. Or combing CT. So we here show the segmentation accuracy over the radiologist. The radiologist is green and the AI is in blue. So you can see the radiologists sometimes missed a lot of regions that is important for the radiotherapy planning. To make our dataset benefit more AI researchers, we have initiated a large-scale benchmark called Touchstone. We invite 14 inventors of AI algorithm to develop their own algorithm in our dataset. So this benchmark is very unique because you almost never heard you ask the AI inventor themselves to benchmark, because you always read a paper said, oh, my algorithm is absolutely better than anyone, but this is obviously biased. So here, all the benchmark, the model is trained by their author. And we as a JHU team, as a third party, to evaluate their model on our private database. And we host this benchmark on Mikai and ISB, and we will continue to host it in the next few years. And we want to really produce the trustworthy AI result and to benchmark the segmentation accuracy, the inference efficiency, and the domain generalizability. And in the first edition, the NUNet team is the winner. The MedNext is it's a top performing model, and there are multiple winners with no significant statistically different performance. So UNet and its variants are very good at medical segmentation, as we all know, and UNet very, very successful. But we certainly would like to see more architectures, such as the transformer, the member, the vision language, and make their best version to beat UNet. And we want the author of this architecture because to join the benchmark, because these guys are really the most people who want their architecture to be successful. So this is the motivation why we would like our benchmark open in a long run to encourage more AI inventor to join our benchmark. We will be really grateful if you could forward this message to the colleague who might be interested in innovating AI algorithm for the medical segmentation. Lastly, we release all this benchmark AI algorithm, and our team ourselves also spend a lot of time and GPU hour to train this very strong AI algorithm on 25,000 and 600,000 image and mask. And we want to evaluate how well the model supervised pre-training compare with the self-supervised pre-training. Because before our data set is out, medical people can only explore the self-supervised learning due to the lack of paradoxal annotation. So this database first time allow people to do this work. And this is our initial funding. We funded the supervised pre-training. It's much efficient than self-supervised pre-training. And we released all the pre-trained model here. It's all trained on by the original inventor of this pre-training strategy. And you can download here, and we will continue to provide the pre-trained model from either our side or the benchmark side to see the community feedback on both our dataset and the AI foundation model to different user case. Okay, that's all what I prepared. Thank you very much for your listening. Appreciate all my colleagues and advisee to contribute to this database, and I hope it's very useful for your research. Thank you.
Absolutely. This is fantastic work, and thank you for sharing this presentation with us. I enjoyed it a lot, and I must really, first comment is congratulations. This is so much work, so much data, so much annotation, and it's desperately needed in the community. It's fantastic. So absolutely fantastic.
Yeah, but I need to warning, it's really difficult work. So try to build the algorithm instead of create this. But we definitely need some innovative algorithm to speed up the annotation.
Right.
It's almost impossible to keep getting up.
Absolutely, and also, selecting the right data set for annotation and so on. When you say that you reduce from 5,000 to 500 by using synthetic data on top, do you need the labels for the 5,000 or only the image data?
I need a label. It's a supervised training.
It's supervised. I know, but for selecting the right 1,500, do you need the labels for
So far, it's a random selection.
You just do random subsampling?
Yes.
I see. So that, and you're not using a dimensionality reduction of the data sets itself or something like that? Because
so far we didn't do that, but I'm sure if you can wisely select the 1500 real sample, it will be very beneficial.
yeah, so if you think of a t-SNE map of all of the data, and then you do some equidistant subsampling,
Yes.
just, I mean, it's a lot of cases, so probably random produces almost the same result. A t-SNE or something like that is probably only useful in smaller data sets. So your sampling strategy is probably similar. At some point you said you have like 100 structures, more than 100 structures that you are able to segment in the abdomen. And then
Correct.
you have 24 masks, you have 25,000 data sets and 600 masks. So on average, you have something like 24 masks per data set. Right?
That is because the CT scan not necessarily the full body, so some structure may not be in the CT.
Okay, but everything that is in the field of view is masked and
segmented.
mutated.
Yes.
Oh, this is so much work.
Yeah.
Amazing.
Right.
Amazing. And one question: when you generate these synthetic samples, you assume that they are correct because you're generating with the segmentation mask as a constraint, as a site constraint, right?
We have, I didn't go into the technical detail. For generating synthetic data, our condition is a mask, which contains the size and the shape and the location. So mask is very informative, and this mask is randomly generated.
I see.
And another condition is text. So text description, because this can be useful to create a specific type of tumor that you want. For example, you want a cyst tumor, or you want the PDAC tumor, or you want the tumor to have a low attenuation or something. So this task is extracted from the radiology report.
And this is also how you can inject new information, right? Because with that, you can for sure generate things that are not part of your training data.
Yes.
So, well, because if you just train synthetic data from the same data that you used for generating the supervised model, then it's not clear where the new information comes from, right? Because
new information, that's actually a good question. New information is come from the background. So as I said, the tumor itself look very similar, especially at the early stage. The only difference is the background. Then this gives me an advantage that I can only synthesize, create the tumor region, then put on top of the normal tissue. Then you can ensure the diversity in this way. So you will not repeatedly give you similar CT scan. You can use a whole bunch of normal CT scan to increase the diversity.
Right. It's a very cool idea, because sometimes you see those suggestions not to inject new, just use the same data and GAN or diffusion model. And but the way you're doing it is very clever, because it really adds new information. While the straightforward, simple approaches, sometimes you wonder how can this be better if no information is coming in.
Yeah, because creating the normal structure make no sense to me, because we have so many real CT scan with normal structure. So what really important is to create the tumor part. And the diffusion model, as I said, is very easy to overfit. That means repeatedly give you same information. Then creating the new normal structure it's actually a disadvantage.
Yeah. It can even lead to deterioration of the model if you add too much synthetic data.
Yes.
Right. Then here's a question. The vision language model, is the vision module limited to 2D slice processing, or do you really have a 3D processor attached?
That's a great question. It's 2D because we do not want to retrain this model. It's a company level job. So we see this model is pretty good. I said it's a high school student level, and our job is to create a task that this model can handle. So that's why we project the 3D CT and the 3D mask into 2D. And this is, I think, is sufficient for the model to make a decision.
Very nice work. Zongwei, I could listen to you for hours. This is brilliant what you're doing, and there's so many technical details that you now omitted that are very, very interesting as well. It's really cool research, and I'm so glad that you presented it here. And I really want to thank you for the presentation, for answering our questions, and congratulations to this great work.
Thank you. Thank you very much.